Okay, so do you hear me well? So welcome back for this last presentation session. We have had a very, very long day, very interesting, but very dense. And so this session is entitled Tools for Xylella fastidiosa Surveillance and Detection. We have had several sessions where we have emphasized the importance of surveillance and detection, and now we have the session dedicated to this. So this session will be co-chaired by Valérie Grimaud from the European and Mediterranean Plant Protection Organization and myself. So we have a very nice session, 6 short presentations, and then a discussion by the end. And so I will invite now Maria del Pilar Velasco Amo from the Institute for Sustainable Agriculture of the Spanish National Research Council for our presentation. And I would like to mention that you have been supported by the EFSA Young Researchers Initiative, and the title of your presentation is Use of Plasmid Profiles in Epidemiological Surveillance. The floor is yours.
So thanks for the presentation, and today I'm going to talk about the use of plasmid profile in epidemiological surveillance of Xylella fastidiosa outbreak in Valencian community. Since the first detection of Xylella fastidiosa in almond tree in Alicante province in 2017, the limit of the demarcated area has been increasing. So nowadays, the demarcated area covers more than 1,000 hectares, of which more than 3,000 hectares are the infected zone. So, so far, only Xylella fastidiosa subspecies multiplex STCs was founded, and this sequence type 6 is completely genetically different from the XTCs from France. And the number of municipalities in the affected zone is 70. So 26 host plants have been found infected by Xylella fastidiosa, and more than 90% of the sample analyzed correspond to Prunus dulcis. In a recent study of our lab, we carry out genome analysis of these 2 strains, the ESBUL and the EVA 5901, that were isolated both from almond trees, and they shared a 99% of their chromosomal sequence, but they differed in the plasmid content. So from now, I'm going to refer as PEUCLA ESBUL plasmid at the small plasmid, and to the PXF64 as the bigger plasmid. Also, this study revealed that they differed in the pathogenicity traits as adhesion force and twitching. So the role of the plasmid in Xylella fastidiosa life cycle is still poorly explored or understood, even though plasmid may contribute to its virulence and adaptation to the new environments and host plant. For that, the objective of this study is develop a PCR-based plasmid typing approach as a tool in the epidemiological surveillance of this Xylella fastidiosa outbreak. Study the geospatial association in the different plasmid profile and implication in the surveillance of Xylella fastidiosa epidemic in the demarcated area of the Valencian community, and to determine if there is a specific or an association of Xylella fastidiosa genotype in the demarcated area according to the location of the sampling, the host plant, and environmental variables. So the primer for both plasmid were decided with the primer blast using the default parameters, and for both plasmid, the limit of detection were determined, being for the higher plasmid, for the big plasmid higher than the small one. So we selected the sample from a total of more than 5,000 infected samples from 68 municipalities of the infected zone, from 20 different host and insect vector, and we select the CQ by Harper qPCR lower than 27, just to be sure that a true negative was a true negative. So this is the host plant that we analyzed. So in total, we analyzed 1,239 samples. And all the samples, all the different host studies share the same genotypes. That is, the most abundant was the genotype with known plasmid. So from the most to the least genotype, the most abundant was the known plasmid, followed by the genotype with the two plasmid, then the small plasmid, and finally the big one. So to be sure that these new genotypes exist in the nature, and to have a strain that is characteristic of this genotype, we did a screening in the strain collection of the EFSA and EVIA. Being the last founded, the EVIA 15574. Now we are doing hard work trying to close genomes and doing hybrid assembling, just to do a comparative analysis between all the genomes. So this is the geographical distribution of the Xylella fastidiosa genotypes. All of these dots are representing from the sample of almond tree. And to be more easy visualization, this is the same representation, but with separated maps of the genotypes. And to study the spatial, the association between the geographical distribution of the genotypes, we do different analyses, as the density plot that shows that there are some areas with a higher density for each plasmid profile, with some overlapping geographical areas among them. For instance, the genotype with known plasmid is more distributed, is more abundant in the south and east part of the demarcated area. The replace function plots shows how is the pattern, the spatial pattern of this plasmid profile. So if they are grouped, randomly distributed, or dispersed. So these all test distance, the actual observed values of the key hat is greater than the theoretically derived expected value for a completely spatial random length. The next step was the bivariate replace K function that compare if two plasmids share the same space. And all tested distance, the actual observed value of the key hat is above the reference line, suggesting that two types of point are more frequently found closer to each other than would be expected under a completely random distribution. And finally, we did a multivariant analysis that showed a relation between the different plasmid profile with the geographic location, the temperature, and the precipitation variables. So here we can see that, for instance, the genotype with known plasmid is in more Xylella fastidiosa suitability index. It's more abundant here, and for instance, related with the highest temperature. And in the opposite, we have the genotype with the two plasmid. So to conclude, the PCR-based plasmid typing approach revealed the presence of 4 different plasmid profiles in Xylella fastidiosa population present in the demarcated area of Alicante, 2 of them being new profile not described up to the date. Spatial point pattern analysis suggests a significant clustering of the distribution of each plasmid profile, with some differences in their geographical distribution, but some overlapping region. Some of the plasmid profiles seem to be more adapted to a specific area or climatic conditions within the demarcated area of Alicante, and further analyses are needed to determine whether this geographical distribution observed at the present correspond the different introduction event for each plasmid profile and subsequent dispersion of them, or the introduction of a single genotype with subsequent loss of those of the plasmid. And finally, thanks for your attention, and also to my lab group.
Thank you, Maria. And our next speaker is going to be Miguel Roman Ecija. He's from Spain for the Institute of Sustainable Agriculture. He's going to talk about early detection of Xanthomonas fastidiosa infection using reflectance proximal sensors in almond and olive trees. And he's also benefiting for an EFSA Young Research Award. The floor is yours.
Thank you for the introduction, and thank you to the organizing committee for having me here and have the opportunity to present this work. Once Xylella fastidiosa is inoculated in the plant, their detection is difficult because mainly to the long incubating period that, joined to the large number of hot plants and the asymptomatic infection, makes very challenging the detection of the bacteria in early stages of the disease. For that, early detection of the bacteria in field is very important and crucial to implement a control measure of the disease and prevent the spread in field. For that, we base in some chemical components that are in plants and their interaction with the sunlight. Once the infection occurs, this we can detect with the devices that I'm going to show you in the next slide. We can detect this small changing in the chemical compounds in the plants that could be related with the Xylella fastidiosa infection and before the visible symptoms appearance. So the objectives of this study was the early detection of Xylella fastidiosa via vegetation indices and pigment content using proximal reference sensors. And we did this in 2 scenarios: in artificially inoculated olive plants in controlled conditions, and in natural infected almond trees in commercial ocar in Mallorca. For both scenarios, we have used these kind of spectral sensor devices, and with some of them we can measure, with all of them we can measure directly in the field, and with some of them we can measure chlorophyll or the content of chlorophyll, flavonoids or anthocyanins, and we can measure the spectral signature of the leaves. And we can calculate with them some vegetation indices that are going to be related with pigments, structural parameters, and other indices that I show you in the slides. For the first experiment in controlled conditions, we have inoculated plantlets of 3 widely cultivars used in Spain, and we have inoculated with these 5 strains. We have measured at several time points and several heights from the inoculation points with the proximal sensor devices, and we have to make sure that the bacteria is in the plant. We have performed qPCR analysis in leaves and stem. In this first slide of results, the main idea is that we don't observe symptoms of the disease created by Xylella fastidiosa. However, we was able to detect Xylella in leaves and also in stems. And also, we saw a significant difference between strains, being the 2 strains with the higher number of plants those isolated from olive. In this slide, I show you the spectral signature of the leaves in plant inoculated by Xylella fastidiosa and the control separated by cultivars. And we can see how the main difference are shown in the blue, green, and the red band. And with this data, we use this data to calculate the indices and do the following analysis. This first analysis, we can see in the clustering how the first organization is between cultivar, and inside the cultivar we can see different patterns from the control plants. And also we have performed a discriminant analysis that allow us to reduce the indices that are going to allow us to discriminate between groups. And this analysis select 42 indices out of 74, with and having a global accuracy, a classification accuracy around 83%. And the main indices that contribute most to this model were related mainly with pigments, and specifically those pigments related with carotenoids, chlorophylls, and xanthophylls, and also some of them of the blue band. With this data, we have performed a canonical plot, and we can see here the points. Each point corresponds to each observation, and we can see a pattern first between cultivar, but between cultivars we can see a different pattern for control and inoculated plant. So with the use of proximal sensor devices, we were able to discriminate between inoculated and inoculated plant, even in absence of symptoms. With once we know which indices works in plantlets in controlled condition in olive, we can figure out which one are going to appear in natural infected almonds in commercial orchards in Mallorca. For that, we have selected several trees from rain-fed and irrigated plots and from asymptomatic and symptomatic trees. We have measured four categories of leaves. On one side, leaves without symptoms from asymptomatic and healthy tree, because we also did a qPCR analysis. And in other side, leaves from symptomatic trees. And between them, leaves without symptoms from branches with or without symptoms, to try to figure out if these asymptomatic leaves have a different pattern to the healthy trees. In this figure, I show you the spectral signature, and we can see how the rain-fed trees have a very different pattern than the rest of the other. And the discriminant analysis reduced to 21 and 12, respectively, for irrigated and rain-fed orchard, and with a classification accuracy of 87% and 73%. And the indice that most contributed to the model was, interestingly, pigments are the same that happen with olive in olive plantlets. But in this case, the interesting thing that there are some of the indices that we can find only in the rain-fed plots and only in irrigated plots. Some of them are charred, and other we can find in rain-fed in this case, and in rain-fed in irrigated almond appears several indices related with carotenoids. In this slide, this last slide, I show you the canonical plot, and for both rain-fed and irrigated trees, we can see on one side those leaves that belong to healthy trees, and on the other side those leaves that belong to asymptomatic trees, to symptomatic leaves. And in the middle we can see those asymptomatic leaves that, and interestingly, the pattern of the leaves that belong to branches with symptoms have a similar pattern to those leaves with symptoms. So the general conclusion is this work was that the physiological response of a leaf to Xylella fastidiosa allow for the discrimination of infectious status in the following scenarios: among cultivar and between artificially Xylella inoculated and control plants on asymptomatic leaves, and between asymptomatic leaves of infected and healthy trees in almond in field conditions. The indices that made the most significant contribution to the models were those related with xanthophyll, carotenoid, chlorophylls, and the blue band of the visible spectrum. So these indices, calculated with a spectral data measure on leaves, could enable early detection of Xylella fastidiosa in asymptomatic plants before the appearance of symptoms, providing a valuable tool for the disease monitoring and plant breeding. Thank you very much.
Okay, the next presentation was proposed by Thomas Poblete, but will be given by Pablo Zarco Tejada from University of Melbourne, Australia, and the presentation title is on detection of symptoms induced by Xylella fastidiosa with high-resolution multispectral satellite data. The floor is yours.
Great, thank you very much. So Thomas Poblete was supposed to give this talk, but he can't be here with us, so I'm very happy to give it myself. So I'll be talking about the detection of symptoms induced by Xylella fastidiosa using high-resolution multispectral satellite data. I'd like to start with a bit of a history behind all the work that we've been doing since the year 2016, when we started a series of campaigns, airborne campaigns using imaging spectroscopy technology to evaluate and to assess whether remote sensing could be used for the early detection of Xylella-induced symptoms. The first flights were conducted in southern Italy, and that was part of close collaboration with Donato Boscia and Maria Saponari's team. That was funded by Ponte project and also by the JRC. That was where I was working at the time. Later on, well, that was also the beginning of the X Factors project that funded the series of activities that were carried out with the data collected as part of those airborne campaigns. Later on, we started flying in the Iberian Peninsula in Alicante. That was funded by JRC and also by internal funding by the Institute for Sustainable Agriculture in Spain, CSIC. And also a series of flights over the Balearic Islands that was funded by the government of the Balearic Islands and also led scientifically by Juan Antonio Navas and Blanca Landa, and I led the coordination of all the airborne campaigns in all the study sites. Back in 2018, we demonstrated that we could detect using airborne imaging spectroscopy, the symptoms induced by Xylella fastidiosa, and we did it with models that performed at around 80% overall accuracy with 0.65 kappa coefficients. And more important even than the 80% was that we could identify a series of spectral-based indicators that were sensitive to the presence of the Xylella, the induced symptoms under biotic stress. And we identified spectral functional groups that were the most sensitive to the Xylella-induced symptoms, but also we evaluated that importance as a function of the severity levels. That overall accuracy of around 80%, which initially was quite good news, we tried to evaluate what was the reason behind not getting higher than that. And there were two main reasons that led us feel that we needed to go and to make some additional progress. One of them is that we could see, and we actually demonstrated with a series of revisits in the field, that the false positives that remote sensing was claiming about infected trees were missed by the field crew. And they were not visually detected in the field. Therefore, we demonstrated, and that was published in the paper, that we could see or detect the induced symptoms at earlier stages, several months in advance. Secondly, we identified a very important issue and a very important problem, which is the biotic and abiotic confounding symptoms, particularly in vascular pathogens where the water stress plays a very important role. And that is a bit of a common sense if we are talking about thousands of hectares that we fly, where we can see on the left and the right-hand side the variability in the right-hand side, the thermal image of a mosaic of more than 1,000 hectares, where we can see the natural variability due to water stress. The variability we're seeing there is not due to biotic-induced conditions. It's actually based due to the fact that the irrigation system is not uniform. The soil properties are different. The infiltration levels are also different across the orchard. The engineering system is not perfect in terms of uniformity and management practices as well. So we evaluated the importance. That was now, I'm talking about 2021. We evaluated and we came out with a protocol that we accounted for the abiotic variability in order to improve the detection power of the models that we were using. In other words, it was critical to identify how the different spectral plant traits that we can quantify using hyperspectral data vary as a function of the water stress that is naturally present if you are scanning thousands and thousands of hectares. There you can see on the left-hand side olive, on the right-hand side almond, and the arrow from bottom to top, it's increasing water stress. And what we show there is that the different spectral-based plant traits change or vary as a function of the stress levels. And that is very important because of that, accounting for that natural variability of the abiotic stress, we improved the models and the performance went up from 80-something% to 94 and from 77 to 92 in almond and olive, demonstrated how important it is to quantify the abiotic variability of stress in order to improve the detection, particularly if you are looking at thousands of hectares of scanning. We did that not only in the context of biotic and abiotic stress, but also across two different pathogens, which are vascular pathogens who have similar effects due to the induced water stress, which is Xylella fastidiosa at the top and Verticillium dahlia at the bottom. So we had a number of questions after that, which can be summarized there, and this is what I like to discuss with you. First of all, whether operational Xylella fastidiosa induced symptoms could be done using existing multispectral satellites that can be accessed by everyone or anyone here. Second, if the new hyperspectral satellites that have been launched or are going to be launched can be used for the early detection of Xylella fastidiosa and any other vascular disease, particularly because some of them are already available, but the spatial resolution is smaller. The first question is addressed in a number of publications that we have using Sentinel-2 data and with one of the commercial satellites like WorldView. The second objective is part of the work package that we are co-leading, in which, as part of Bexil project, where we are going to be using hyperspectral satellites for that purpose. Here you can see on the left-hand side the airborne hyperspectral data that we normally collect using our airborne system, flying in Italy, Spain, anywhere, getting around 40-50 centimeter pixel sizes. On the right-hand side, what you see is the commercial high-resolution multispectral data that we would collect with a satellite sensor currently available. It's at the limit of what we can do in order to identify single tree crowns, but still we can see the trees individually that would allow us to extract the spectra. It's on the spectral component, the spectral side, where we are missing most of the information, because on the left-hand side is the hyperspectral data, more than 200 spectral bands in the visible near infrared. On the right-hand side, we have 8 spectral bands at specific wavelengths. In all these projects and publications, we have proposed a methodology which is a combined mechanistic with empirical models. A mechanistic model uses derived transfer models to quantify plant traits, linked to machine learning models that evaluate the importance of the different plant traits, structure, photosynthetic pigments, chlorophyll fluorescence, and transpiration, and spectral indicators in order to account for all those aspects and all those inputs in order to make the disease detection as accurate as possible. Results are shown as a summary in one of the figures of the paper, but you can see here one of them. We go from early to intermediate to asymptomatic versus all levels of severity, and we show the overall accuracy in red and the kappa the overall accuracy in blue and the kappa coefficients in red. And we show it for different scenarios. We do it for hyperspectral and thermal data, if we could collect both at the same time, hyperspectral only, if we don't have thermal data available, commercial satellite at high resolution, if we also have thermal data available at the same time, and only only multispectral data. What we can see is that in the best scenario we reach this 80% that we were talking about before. When we go to the early detection and we only have the multispectral satellite, our kappa coefficients are dropped by a lot, and they go down to very low values of below 0.3. As a summary, and it's one of the messages here, when we deal with hyperspectral data and we account for the abiotic-induced variability, we are reaching easily more than 90% overall accuracies. If we go to 12 bands multispectral images, we go to around 70%. But if we do what most of the commercial companies offer, then like RGB cameras, then we go to roughly a bit more than 60%, which is a little bit more than just flipping a coin. Just the last conclusions, the easy take-home messages. Intermediate and advanced stages of the disease can be detected using multispectral satellites which are currently available. So this is good in terms of whether in some cases we are interested on the intermediate or advanced stages. Once the infection is established, if we want to evaluate the spread using currently available operational satellites. If the objective is the early detection, the multispectral sensors fail and hyperspectral is needed. Why is it failing? Well, it's failing because of the number of spectral bands. Not only that, it's not the spectral bands itself, the number, is the fact that the specific spectral bands that are needed for the early detection are related to the solar-induced fluorescence, to the NPQI in the blue, to the anthocyanins, and to the xanthophylls. And those are particular traits where multispectral sensors currently available don't have a spectral band sensitive to those traits. So it's not the number of bands only, it's where those spectral bands are located. Finally, current work and future work will be based on using the new hyperspectral satellites, where we have full spectral bands in terms of numbers covering the full spectrum, but the spatial resolution will play a role, and particularly in non-homogeneous or heterogeneous canopies, discontinuous canopies, that's like most of the orchards, that will be a challenge that we will have to evaluate. Thank you.
Thank you, Pablo. Our next speaker is Alice Del Bianco, and she's going to talk about Repest. It's a tool which has been developed by EFSA for designing more robust and harmonized pest surveys in the EU. The floor is yours.
Thanks, Valerie. So good afternoon. So since 2017, EFSA is working on a mandate of the European Commission to provide the member state with a toolkit for planning and execution of statistically sound and risk-based surveys of quarantine pests. So we have developed our pest survey toolkit, which includes several outputs and tools. For the survey preparation, we have published so far pest survey cards on around 100 pests, plus the big group of non-Eutrophritidae. And those cards include information on where, what, how, and when to survey for those pests. For the survey design, we have developed general guidelines plus specific guidelines, including those for Xylella fastidiosa. And those guidelines guide the users in setting the survey parameters, so the method sensitivity of the detection methods, the structure and the size of the target population, and the confidence level and the design prevalence, so the aim of the survey. The toolkit also includes a statistical calculator, Repest Plus, to estimate the sample size. However, RIBES Plus is a generic statistical calculator in which there is no step-by-step guidance. So we were asked to further develop this tool and to tailor it to the needs of plant health. So we are now going to release RIPEST, that is the new RIBES Plus. RIPEST is tailored to plant health. It is freely accessible. You have just to register to the R4U EFSA platform. And RIPEST guides the user through the entire survey process. So from the initiation to the preparation, the design, the implementation, until the conclusion. So there is a step-by-step guidance. So I'm now going to show you how RIPEST looks like with an easy example on Xylella fastidiosa. So imagine we want to plan a survey for Xylella. We have first to choose between detection, delimiting, and buffer zone surveys. In this case, I choose detection survey. The second step is to choose the pest. In this case, of course, is Xylella, but RIPEST works for any quarantine pest. So you can also add additional information on your pest, for example, the status of the pest in the target population and when you have conducted the last survey in the same target population. Then we have to define the survey area. So we have to choose a member state. In this case, I choose, as example, I choose Belgium. And then I have to select the NUTS level. I choose NUTS 2, so provinces, and specifically, as example, 3 provinces in Belgium that you can select from the drop-down list or directly clicking on in the interactive map. Then the following step is to divide the target population and define our epidemiological units that can be administrative units, so NUTS levels, land use categories, or both. For this example, I choose both administrative units and land use categories. So I divided my 3 provinces in Belgium in forest, agricultural, and urban areas. So in total, I have 9 epidemiological units. And for each one, I have to insert the number of host plants of Xylella fastidiosa that are present in each unit. And I put here some numbers. Of course, this is just an example. And then I have to define my detection and identification methods, so the procedure that I will follow in the field and in the lab. As example, I choose in the field to select my inspection units, my plants, based on visual examination of symptoms, and my sampling matrix will be leaves. My sampling effectiveness, I set this value at 70%. In the lab, I will test my plants through ELISA, followed by qPCR, for example, and I set the diagnostic sensitivity as 78%. So those 2 values, of course, can vary, and I took those 2 values from the EFSA guidelines that we published in 2020. Of course, this is those values has to be set by the users based on the specific situation. We have also a poster about that, so if you want to know more about how to maximize the method sensitivity, you can have a look to the poster prepared by our trainee, Marina Martino. And then I have to set my confidence level and design prevalence. Here I put 95% of confidence level and 1% of design prevalence. Now I can calculate and estimate my sample size. So RIPEST will calculate the sample size, and so here I get my theoretical sample size, so the number of inspection units that I need to sample in the field and test in the lab for each epidemiological unit. At this point, we have our numbers, and we can go for the survey implementation. So I can go in the field, take my samples in the lab, I test them, and to get the results. Of course, I didn't say it before, but you can stop, you can save your project in repest in any stage and come back in a later time to continue with the work. So let's imagine that I've been in the field, in the lab, I have my results, and I come back to repest, to my project, to make my conclusions. So was the pest found during the survey? Hopefully no, I didn't find it. And I have now to insert in this table, in which there is the previous theoretical sample size, the real numbers of negative and undetermined samples that I got. So here again, I put some numbers as example. And now I can calculate the achieved confidence level that I reached, and so my conclusion. And repest will calculate for you the conclusions. So in this case, the survey area is free. So my 3 provinces in Belgium are free from the pest based on a survey with a confidence level of 95.63% and a design prevalence of 1%. So I reach my conclusion now, and I can download the entire report that can be downloaded in Word document and, very important, in Excel, in an Excel file that has exactly the structure, and it's already pre-filled with all the data that the member state then need to upload in the Eurofit survey platform. So I think this functionality will be very appreciated by member states, so they can just download the Excel file here and upload it directly in Eurofit survey platform. Repest has many other functionalities that I didn't show here because there is no time. It will be pre-filled by a relational database containing for all the union quarantine pests for which we have a survey card, the information that are present in the survey card. So for example, host plants, detection methods, etc. So for each quarantine pest, you will have drop-down list. There is the possibility to add risk factors, so to plan a risk-based survey. This is very useful because adding risk factor, you will be able to reduce the overall sample size of your survey because you concentrate in areas in which you have higher probability to find the pest. And again, we have an example in our poster. There is the possibility to reallocate sample within epidemiological units, upload shapefile, and many more functionalities. What's next? So we are working in developing the pest survey cards for all the union quarantine pests until 2027. This autumn, we will release the relational database together with repest and also a manual and the updated general guidelines. And at the end of this year, we are also going to release another approach for conducting surveys. It's a multi-pest survey at crop level. So here the focus is not the single pest, but the entire crop, and we are piloting this on citrus, potato, broadleaf trees. We are also working a lot on communication trainings. We are organizing workshop, e-learning course, webinars, and also we are going to run several expert knowledge elicitation to provide values for the method sensitivity and the level of prevalence and detection for the priority pest. That's it. Thanks for your attention. I would like to thank all my EFSA colleagues and the experts of the working group of pest survey methods. We have here some of them. Thanks a lot.
Okay, thank you, Alice. So the next talk will be given by Pauline de Gerfagnon from the French General Directorate for Food, Ministry of Agriculture, and French Epidemiological Plant Health Surveillance Platform. And the talk is on delimiting survey of Xylella fastidiosa subspecies multiplex. The floor is yours.
Thank you. Good afternoon. So I'm very glad to have the opportunity to present the work realized in the framework of the French Epidemiological Plant Health Surveillance Platform in order to define a delimiting survey of Xylella fastidiosa subspecies multiplex in the region Occitanie. So as you know, Xylella fastidiosa is present in 3 regions in France. Since 2015, it's present in Corsica and Provence-Alpes-Côte d'Azur. And since 2020, we have detected Xylella fastidiosa subspecies multiplex in the region Occitanie. So indeed, in September 2020, we first detected the bacteria in the department of Aude on Lavandula intermedia on a production and retail site of ornamental plants. Eradication measures and surveillance were immediately implemented according to the EU regulation, and the reinforced surveillance led to a rapid extension of the demarcated area. 1 year later, the demarcated area was over 90 kilometers from west to east and 25 kilometers from north to south. That's why the risk manager, the French Ministry of Agriculture, asked a multidisciplinary working group to support with further delimitation of the contaminated area. So to do so, we meet a working group of over 25 people with complementary expertise at the national and at the local level. We realized on-site observation in demarcated areas and in pest-free areas. To determine a risk-based survey, we realized risk maps in order to determine for each at the resolution of 2 kilometers, of square of 2 kilometers, the risk of establishment of the bacteria in the region Occitanie, using land use and ecoclimatic data and different model based on Euclidean distance and on the MES algorithm, taking as reference the positive squares in France, so in Corsica, Provence-Alpes-Côte d'Azur, and Occitanie. And then we used model averaging. So I'm going to present the different results we obtained. During the on-site missions, the working group could observe that in the infected areas, the bacterium appears to be widely disseminated in the semi-natural and natural compartments, with 2 plant species identified as indicator of its presence, Spartium johnseum and wild almond Prunus dulcis. Moreover, we observe that agricultural wasteland and semi-natural areas close to infrastructures have been identified as environment favorable to spontaneous and pioneer vegetation susceptible to the bacterium and its vector. At the same time, so we conducted works to define this establishment map of Xylella fastidiosa. So it's a map on a grid of a resolution of 2 kilometer squares. And you can see the risk, so the darker the color, the higher the risk is. The working group assumes that the presence of the bacteria could be beyond the area already found contaminated. So out of the red plots you can see. And that's why we have drawn a 10 kilometer wide boundary ring positioned 35 kilometers from the contaminated areas. So on this boundary ring, you can see in yellow on the map, we have adopted a sequential adaptative strategy from Lazzaro et al. So the first step was sampling on 182 squares. We defined this sampling according to the tool Rebus Plus of EFSA and the different risk classes. And in this first step, we made almost 9,000 plant samples, mainly from spartium and symptomatic samples, and a total of almost 2,000 analyses. During these first phases, we found 6 positive to Xylella in 4 different 2-kilometer squares, corresponding to 2 sectors on the boundary ring. During the second phase, we found, so it was on 500 meter squares, we found between 1 and 10 positive samples, and the third phase is ongoing. So on this map, you can see all the samples collected during Xylella surveys in the region Occitanie since 2019 and the positive samples. You can see in the middle the first detection which occurred in 2020 and 2021. And then you can see, so in dark yellow, the 2 sectors we found during the delimiting survey. And you can see all the samples on this boundary ring we have detected. You can also see that we have found in 2022 other contaminated sectors out of the boundary ring in the framework of official surveillance and plant passport inspection. So to conclude, these are the result of a constant improvement of the risk analysis and of the complementarity of the different survey types: detection survey, monitoring, delimiting, and also event-based survey. It was used at the national level to reinforce the surveillance in the wild and semi-natural compartments in pest-free areas. And it's also used to adapt better the survey and the management strategy to the different outbreaks, and it's still used in Occitanie for this campaign. This collective and multidisciplinary approach was very useful for the risk manager to give a rapid answer to this question of delimiting an outbreak. And during this mission, we also identified remaining questions to the research, like the origin of the presence of the bacteria in this region, the behavior of the vectors, and the impact of climate change and water stress. So I would like to warmly thank all the members of the working group and all the people we met on the field during this work. If you want to know more about the activities of the French epidemiological plant health surveillance platform, a poster will be hanged during the ICPP. And I thank you all for your attention. Thank you.
Thank you, Pauline. And our last speaker of the day is going to be Martina Sendoya. She's from the Valencian Institute of Agricultural Research in Spain. And she will present you us evaluation of the outbreak response plans for Xylella in Alicante, in Spain.
Okay, thank you for the presentation. Then I am going to present this work in which we evaluate the outbreak response plans for Xylella fastidiosa in Alicante. Xylella fastidiosa is a quarantine priority pest, therefore is under strict phytosanitary measures and specific control measures. These control measures are regulated by the Commission Implementing Regulation 2020-1201, which includes contingency and action plans and also mandatory annual surveys. These surveys must be done following the EFSA guidelines for statistically sound and risk-based surveys. We have focused on the affected area of Alicante, where Xylella is the cause of almond leaf spot disease. And although molecular epidemiological studies suggest the first introduction in mid-19s, the first detection was in 2017. Therefore, until this date, non-interventions have been applied in this region. The objective of this study was to compare different outbreak management plans, including surveillance and control strategies under different settings, including those established by the regulation, and also evaluate effectiveness and efficiency of them. To simulate disease spread, we have based on a spatial individual-based model where the probability of a susceptible tree becomes infected will depend on the transmission rate, which is reduced for the asymptomatic trees, and also on the spatial correlation between the susceptible tree and the infectious trees. This model and the parameterization was set based on a previous study, which is available and open access from now as a preprint, and also the code in Zenodo. As the baseline scenario, without any interventions, we designed the distribution of the almond trees based on the official surveys and also on the geographic data of almond plots. We start with an initial outbreak of 5 foci, and this pattern hypothetically can be represent an introduction of propagating plant material. We simulate the disease spread over 30 years in monthly time steps. And in this scenario, without interventions, which will serve as a reference for later implemented outbreak management plans, after these 30 years, we have more than 90% of the population infected. Then, from this initial outbreak, from one side, we will have this baseline scenario without intervention, and in the other side, we will have the outbreak management plans. In these outbreak management plans, first, the surveys will be implemented each year as following the legislation, and first we will implement a detection survey in the whole study area, and based on the detections, we will delimit the demarcated area, which consisted in an infested zone and in a surrounding buffer zone. In the infested zone, the eradication will be applied, and in the following year, surveys must be done in the buffer zone, and also detection surveys again in the non-demarcated area. Also, the buffer zone surveys will be more intensive. To calculate the sample size, we have based on the hypergeometric distribution, which depends on the population size and 3 intercorrelated parameters, which are the confidence level, design prevalence, and the method sensitivity. And also we have applied 2 approaches for the surveillance, which are detailed in the EFSA guidelines. In the one-step approach, the sample size is calculated based on the total number of trees, and in the 2-step approach, the study area is divided in grid cells, and in the first step, we calculate the samples per cell based on the mean number of trees per cell, and in a second step, we calculate the cells to be inspected based on the number of cells. Then we have implemented 48 combinations of the outbreak management plans, including these 2 approaches for the surveillance, each one with 2 confidence levels, and also 2 sites for the buffer zone, 2 sites for the eradication, for the eradication, and in bold are the minimum established by the legislation. And also we have included this transmission rate reduction in the buffer zone, which can be interpreted as in line with Donato Borsia presented this morning, with other control actions as control vector or the effect of inoculum reduction. As a result of these combinations, in terms of effectiveness, which we measure as the reduction in the percentage of infected trees, well, in this first box we have the combinations with the 1 step, and in the second box the combinations with the 2 steps. And the red line is the baseline scenario without interventions. Then all management plans are effective in the reduction of the infected trees, but with the 2-step approach we have better results, and also with a high confidence level for the two surveillance approaches. But in terms of efficiency, measured as the increase of the percentage of susceptible trees not eradicated, we can see that many combinations of these outbreak management plans have the same result as without any intervention. Then, but in this case, the reduction of the transmission rate in the buffer zone have a higher effect. I don't know if you can see well, but in all combinations, the best result is with the higher reduction of the transmission rate in the buffer zone. Also, here we have better results with the 2-step approach. However, in terms of survey effort, that is the number of samples per year, high difference are with the 1-step and the 2-step approaches. Here are represented separate because they have different scales. With the 1-step, we have 500 or 1,000 samples per year, and with the 2-step, we have between 15,000 to 27,000 samples per year. However, in terms of inspection intensity, that is the number of cells inspected per year, we have similar results with the 1-step or 2-step approaches, and only depends on the confidence level. As a conclusion of this work, surveillance is the key for the performance of outbreak management plans. 2-step survey approach was more effective and efficient than the 1-step approach, but survey effort was much higher in the 2-step approach. Similar inspection intensity was obtained between the 1-step and 2-step approaches, and transmission rate reduction in the buffer zone increased the efficiency. And thank you very much.
Thank you, Martina. Well, now we are going to take questions for our 6 speakers. Yes, here.
Thank you. I have a question for Maria. Do you know the size of your plasmids? How big they are in Xylella? And also, what kind of genes are present inside this plasmid?
Yes, the small plasmid has a size of 1,000 base pairs, and the big plasmid has more or less 58,000 per base. So the small plasmid is really small, but the genes that when we did this work comparing the genome, doing the genome analysis, we realized that we have 51 coding genes, and some of these genes are related with the pathogenicity traits.
Thank you.
You're welcome.
just in the front.
A question for Miguel. So, how much time did you gain with your, in terms of early detection with respect to qPCR, with your proximal months or I don't know?
Yeah. Okay, that's a very good question, but we don't know for sure yet. In last year, we did another survey, another measurement campaign, and we take like 2 or 3 months early. We can detect some of these plants that we have measured in May, that they are going to have symptoms at the end of July, in almond.
Don't see any other question. Yeah.
Hi, Rodrigo Almeida, UC Berkeley. I also have a question from Maria de Pilar regarding the plasmids. So at the very beginning of the talk, and it's really cool to see plasmids used in that landscape component. You have the 2 strains, right? One that has the plasmid and one that does not. Did you try to get the plasmid from the one that has the plasmid and put it into the one that does not have the plasmid? Thank you.
That's a really nice experiment to do, because I tried natural competence in this strain, and this strain didn't catch DNA. So maybe with electroporation or conjugation or other ways to transform this bacteria, could be possible, but it's a really good experiment to know if this bacteria is be able to catch this plasmid.
The question was more if the phenotype is reproduced once you do that. But anyway, those are all ideas. That's cool.
That come to the interest of mine, because I work on this plasmid earlier. Did you ever look at the diversity of this plasmid? Because from different strains, the size can be different, and all kind of variations from different strains. That's what I wonder if the primers, but look like it works, but there's some question there.
Yes, for this reason we are doing the sequencing, because we really want to know if there is any difference in this plasmid, and also if it's related with this spatial distribution of this plasmid.
Did you see the variation? That's what I'm asking. Different sizes.
We still are sequencing the genome, or what do you mean?
Oh, a number of them already in GenBank of these 1.2 kb plasmids.
Sorry, say again.
In GenBank sequence database, there are a number of the 1.2 kb or the related sequence there already.
Yes, the small plasmid is really similar to the subspecies fastidiosa, the Peucla plasmid that is in a lot of fastidiosa strain, and also the big plasmid is similar to the hibiscus strains.
Okay, thank you.
Okay, I have some question about the detection, remote detection. So to Miguel, I would ask, in which practical circumstances you think the reflect and proximal sensor could be useful, in which kind of outbreak type? So it's place you never found Xylella, or it's a place you already have Xylella, and you want to know which trees are infected or not.
Yeah, it's a good question. I think it can be both. I think it's like you can use this as another tool to complement the other kind of proximal sensing, and also complement this with surveillance campaign.
But in practice, do you have to have one sensor per tree, or how does it work?
Sorry?
How many sensors you need to put in a nectar for this?
I don't know. I think it's another tool that we can use for try to get the early detection of the disease.
And then the other question would be the same topic. Then I would say that if we use the satellite simple system, that in reality you cannot detect the very early stage, what is the use then of that system? So you could use satellite maybe to find area which are already advanced, but for some reason, maybe it's mountain area or isolated area, not so well monitored, and then nobody has looked at. So for example, if you look the satellite data for Corsica or Balearic Island, where you have this but now it's quite widespread, you think we could have found the Xylella earlier than by the actual monitoring?
Yeah, I think that everyone here is interested on the early detection and the pre-visual assessment, and this is what we all want, and we have demonstrated that to do that successfully we need either hyperspectral data or specific spectral bands in sensors that are of multispectral specs. I remember when I was at the European Commission, one of the questions that we were asked is how many trees are affected in the European Union. And it was difficult to answer the question at the time, and because the only option was to take aerial photography and assess trees at 2 different times and check how many trees looked infected. I think that the multispectral satellites that we currently have will not answer at this moment the early detection and the pre-visual, but could be used to assess how many trees are affected at least intermediate stages. That is something someone could argue, well, you don't really need satellite because you could walk and do it one by one. On the other hand, if we are talking about millions of hectares, like for example the buffer zone in Italy or in other countries, in other pathogens as well, I think that multispectral satellite could provide a good visual, extent of how many trees and how much area is infected and evaluate from year to year how much is changing.
So in practice, we have now a system for detection by image analysis, which you can use in advanced epidemics to see what situation, maybe with more sophisticated sensors for the buffer zone for specific area, or you could use in orchard area. So fundamentally, we have very different instruments we could use according to the needs.
Exactly, and I don't think that is one or the other. It's like when sometimes there is a discussion about is it better drones than airborne or satellite? I don't think it's one or the other. Depending on the scale, depending on the type of outbreaks, we can fly a drone with a hyperspectral sensor, or we can fly with a multispectral camera in a limited small area, or if we want to fly thousands of hectares with a plane around specific outbreaks, we can see whether around the true positives, we find trees that are not yet showing symptoms, visual symptoms, but can be detected with airborne hyperspectral data. And on top of that, we could have satellite data that is monitoring continuously the spread. But obviously looking at intermediate stages, or at least evaluating and quantifying how many trees had initial symptoms, and then how much is changing from season to season, for example, to evaluate and to quantify how many trees are getting into more advanced stages. So I don't think it's one or the other. It's a combination of all the technologies that we have, depending on the scale, the type of outbreak, and the type of technology that we can operate.
Maybe another question, very naive to Pablo and Miguel. So how far are we from, let's say, helping at improving sampling efficiency by the techniques you explained? So is it already, let's say, ready to use? Let's imagine, for example, I have a hotspot in Greece, and I'm suspecting that maybe Xylella is there. How could we connect the technologies that you explained and help people who have to deal with surveillance and sampling on the spot?
Yeah, so the technology is here. It's already available. It's only a matter of a bit of knowledge and experience about how to fly and how to operate imaging spectroscopy or specific multispectral cameras. So we can deploy any of these sensors anywhere, and some companies offer services, mostly in the multispectral and lower level type of technology. But scanning a few thousands of vectors and then evaluating hotspots using clustering methods and algorithms that we are developing is possible. Once you have evaluated or found specific hotspots, then you can send people to the field, to those specific trees showing symptoms in the image, to do field assessments and to take leaves to the laboratory for evaluation. I'd like to add also, in terms of the proximal sensing, because it's extremely important that when we evaluate the physiological changes of plants infected, we always start at the leaf level, because starting at the leaf level means that we understand the physiological changes. Because if we don't see any change at the leaf level, it's better not to look for changes at the image level, because at the image level we will reproduce the changes that we are observing at the leaf level. So that work is extremely important, also for validation purposes. In any of the works that we have published, we not only fly and evaluate with either visual assessments or PCR, we also identify trees, and in those trees we do leaf level measurements with proximal sensing. So that way we validate what we see in the image with the field level data to make sure that what we are seeing from the image is real and corresponds with the leaf level assessments that we can make.
I'm going to say kind of the same, that proximal sensor devices serves a validation also of the flight of the multispectral images. Thank you.
Yeah, but my question is for Martina. Maybe you are continue with the. Okay, yes. So Martina, thanks very much for your nice presentation. Maybe you already said, but I missed during your presentation. But it's clear that you have very different results using the one-step approach or the two-step approach. So, but advantage and disadvantage of each of the two approaches. But which one would you recommend in a practical way? Yeah, I know that it's difficult to answer, but you are the expert.
No, well, I cannot recommend one or other. I see the advantages or disadvantages. The two-step approach, with the two-step approach, we have better results. Also, I didn't see before that with the two-step approach, only with this approach, we have the reduction of the infected trees 0, and with the one-step not. But the high cost of the two-step approach is very high. Then it depends on many things. Yeah.
Okay, thank you.
I have sort of following up a question to Pablo, and I think we have to be quite smart how we do the detection, and especially in Australia, I think detection and making sure that we're on the top of it is extremely important. And I think you sort of answered the question partially, but having access to hyperspectral or way of identifying potential infected trees, or infected trees in this case, when you have like high level of detection. I'm just wondering, do you have to have like positive or negative checks to account for, let's say, time of the year or geographic region? So I guess my question is, how easy it would be to take those references that you have collected in Europe, let's say Italy, Spain, and whatnot, and adopt that in Australia. So, for example, for screening of trees in Australia, where we don't really have the positive references yet.
Yeah, sure. No, it's a relevant question. So we had a project with the Department of Agriculture in Australia as part of the preparedness program. And the whole idea was that all the algorithms and what we have learned in Europe, how easy it will be to apply it into the Australian situation as soon as possible if there was an outbreak. So the approach that we've started with the first flights in Italy and continue with Alicante and the Balearic Islands have been done in a way that instead of developing black boxes, like, for example, machine learning, where we don't really understand what's going on, our approach, I talked a little bit about it, but not in depth, is that we quantify plant traits which have physiological meaning. By that, what I mean is that we don't just use the spectra as input to build the algorithm, then applied to the image, because that would be site-specific. And site-specific means that it would work very well in my field, in my orchard. I would get 95%, but then I go somewhere else, I mean, not even to Australia. In Spain, Italy, or any other, I go to the neighbor and it would fail, just because the optical properties of the orchards nearby could be different, because the planting grid is different, because the percentage cover is different, because the leaf area index of the trees is different, the age, the background, the management, the pruning, I mean, all different aspects. So what we do is to quantify plant traits with physiological meaning. So we quantify each tree, how much chlorophyll, coronoids, xanthophylls, anthocyanins, chlorophyll fluorescence, and structural traits. And then we use those traits to build the model. So that model is in some way applicable anywhere, because we are not really looking at the spectral optical properties of each orchard. We are looking at the actual physiology and the physiological changes happening under infected conditions. So, I mean, we don't know if there's an outbreak in Australia or somewhere else. We could take our own algorithms and then apply there. We already did a bit of work flying healthy orchards with variability in terms of nutrients and water stress, and we added to the algorithms, so they are in some way ready for the varieties, some of the varieties that we have over there. Now, obviously, after first scans, we will have to validate it, either with visual assessment and PCR, and rebuild the models to improve the accuracy. But they are in some way applicable anywhere, because we look at the physiology, we don't look at black box signal-driven models.
Pablo Zarco, a practical situation, a real situation in an orchard setting, in which you have all the plants that you know they are infected. And you are testing...
All of them infected.
I say not for early detection. I'm not speaking for early detection. I'm speaking of testing products to make better condition for plants infected. So what do you recommend as a physiological, even with a drone, or as a physiological indicator with a drone to evaluate the effect of, I don't know, promoting a better resilience to Xylella, thermal or hyperspectral or multispectral?
Yeah, so
it's a simple one.
Yeah. So I think what I would suggest is that what we want is to evaluate the performance and the plant condition, and the plant condition, it's done or it can be quantified using looking at transpiration rates and photosynthesis. Transpiration rates through canopy temperature, photosynthesis through chlorophyll fluorescence, and photosynthetic pigments, biochemistry. So the best would be to use hyperspectral data to quantify those plant traits that are related to the physiological and performance and the plant condition. Depending on what you have, different things could be done. If what you have is a drone with a couple of multispectral cameras with 12 spectral bands in total, what we would do is to evaluate a specific vegetation indices sensitive to those biochemical constituents to evaluate in relative terms the effects of the different products that you will be applying.
Thanks for the nice presentation and the session. My question is for both Alice and Pauline. Very easy question. As Belén pointed out this morning from the Commission, now as you know, Xylella, many of the outbreaks in the EU were thousands of hectares of extent when first detected. So now the policy of the Commission is to improve survey, co-funding with the EFSA guidelines. But we see that the implementation of these programs are at the cost of maybe increasing the sample sizes and the resources, etc. So I know there are a lot of interaction now between EFSA and the MPPOs. So where we are at this moment, I mean, from the people that is developing the methods and the people that have to apply these methods, so in the practical terms.
Maybe work. Do you hear me? Okay. Well, maybe I can start to reply. We have just started a new network of member states in EFSA. We have had the first meeting in May, so to transfer the new tools, the new guidelines directly from EFSA to the member states. So this is what we are doing now, and we are also, as I mentioned in the last slide, we are now going to work a lot on communication trainings, so we are going to prepare webinars on RIPES, on the new guidelines, also not only Xylella but on the other priority pests, and webinars, e-learnings, etc. So this is what we are doing now. We trying to transfer what we developed directly to the representatives of the member state with this network on specific for surveillance. And Pauline was also in this network.
Yes, so from my part, we try to use most of the results of research and expertise to improve our surveys. And also on the management strategy, so as you've seen in, for example, in Occitanie, it's always spreading. So we are also wondering how to manage this in the long term and how to develop strategies which could be more effective to the situation we can observe on the field. But there is also the regulation framework, so we have to take everything into account.
Well, I think it's time now to close our session. I would like to thank you all for your questions, very interesting questions, and also thank you for all 6 speakers for your nice presentation.